Ahmed KasimuJuma from Federal Polytechnic, Bali. Thank you, first of all, thanking the organizing committee for giving me this wonderful opportunity to present a paper titled Batch-stochastic Sub-gradient method for solving non-smooth convex loss function problem. An optimization problem is often of the form either to minimize the cost of production or to maximize profit. So we want to take regression analysis into machine learning techniques. So here we want to minimize the parameters B, W1, W2 up to Wm. So we say this equation 1 can be solved using model parameter. And one of the tools that we often make use in estimating model parameter is loss function. And among the loss function, there is a loss function that we call mean square error, which is one of the discovered loss function as regarded as L2 loss function. So we said if we adopt mean square error, then we can minimize B, W1, W2 up to W1, that is our parameters, using gradient descent. And we said there is also there is also another loss function called mean absolute error. And if we adopt mean absolute error, which is this loss function that you have at the top here, then learning, or we can optimize parameter B, W1 up to Wm using sub-gradient method. So here, we will get to know that, or realize that mean absolute error is regarded as L1 loss function, that is first discovered loss function. But scholars observe that at the optimal feasible region, we have a non-differentiable point. So scholars doesn't have way then on how to find the value there, the loss function there. So then they created the L2 loss function that is called for mean square error. So after they created mean square error, they discovered that it used to attract some noises. So for that, they say, whatever value we have as a MSE value, then let's take the root of that value to penalize the noises that we attracted. So they generated they created what we call root mean square error. So during our research, we discover that's why all these creating MSE and RMS, that is mean square error and root mean square error, MAE, that is the first discovered loss function, is the best among all the L2 loss function. So we said, let's adopt MAE, bearing in our mind that at the optimal feasible region, our model space is non-smooth. So let me take us back a little for us to get more clarity of what we are doing. For example, assuming you have house in square feet, and this is for the first column you have 1,000 square feet, and the price, that is the second column, is 150,000. 2,000 square feet, 400,000 as a price. So that one is what we call the real data that we have. So if we plot it in a graph, we'll get to have, that is the second figure there, the down figure. We are going to have what we call the real space. So observe, if you try to draw a line that will pass through all these data points, we'll discover that some data point will be out of that line. So what machine learning does, it will initialize a point at which our line will intersect y-axis, and it will take an angle. B, the B that we are up to, and what have you, B is the what? It's the intersect of y-axis. Y, the W are the angles. So it initializes of that. If we pick a line like this, which is far from the what? From the data point, So meaning we have to what? We have to do some learning before we what? We reach a best fit line. That is to have a line that is less error from each data point. So we say if we adopted MSE, then at the model space for single parameter, we are going to have something like this. And the solution is the bottom part here, which can be reached using gradient descent. So again, we say if had it been we adopted the L1 loss, that is the MAE, which we have interest on, then we are going to have a model space of this nature, which at the optimal feasible region, it is non-smooth or non-differentiable. So we said mean absolute error is more robust to outliers. That is, if you have one outlier or many outliers. In case of MSE, one outlier can generate some noise. But in case of MAE, it will penalize that outlier. Reason is this. If you look at the equation 2, that is the MSE, you will see square the value there. So it is telling us like it's taking the total area there. Whatever value we have, we are squaring it. But MA is taking the absolute value. So that's why it penalizes the outliers. That's why we say when you use mean absolute error at the global minimum, the function is non-smooth. There is a need to develop a generalized gradient method, which is called sub-gradient method, that will solve non-smooth convex loss function problem with improved accuracy and efficiency. During our research, we discovered that several authors have discovered the setback of mean square error and root mean square error. But despite discovering that, they continue to use MSE because MSE has differentiable property. You can differentiate. Because it has that square, you can drop down that square. But MAE is more of a non-sensitive to outliers, but it has non-differentiable properties. So we said we want to develop a batch-stochastic sub-gradient method. Sorry, let me take it. Batch sub-gradient is non-smooth convex probe, but it is consuming time. So, like that record that I have shown earlier, where we have house in square feet. For 1,000 square feet, the price 150. So, when we want to give a machine to learn and give us the best fit line, there are two prominent methods that scholars use to go in trying to find the optimal parameters. The first method, they call it batch method, while the second method, they call it stochastic method. The first method, batch method, used to consider the entire data set. You have 1 million records, it will consider the entire record. It will load all those 1 million records in memory. Then it start initializing. At which point will my fit line intersect the y-axis, and which angle will it make? Then it's continue its initiative, it passes through the optimal feasible region. And there is method that we call stochastic. Stochastic will consider one data point at a point. So for that, we say stochastic method used to attract noise, but we don't have issue of memory. Because we say batch used to consider the entire data set at once. You have 1 million record. Which kind of software can, as a matrix, because all what we are doing, we used to take it matrix into the computer, can take 1 million record as matrix size. So we said batch sub-gradient method will give us the stable parameters, but we are having issue of memory. While stochastic, we don't have issue of memory, but since it is considering one data point at a point at a time, that make it to attract noises. So we said we want to take the good features of batch and the good features of stochastic, then apply it and see what it will give us. The aim and objective of our study. We said the aim of this research to develop a batch stochastic sub-gradient method for the direct solution of loss function problems that are non-convex. And the specific objective is to reveal the mystery behind sub-gradient in conjunction to machine learning. Determine the efficiency of the method. And our scope is we want to consider a loss function program that is what? Convex. Significance of this study. We have discovered that this field of sub-gradient is unfortunate to be blessed with several high-quality, comprehensive research level monographs. And we have discovered that there are many variations of sub-gradient method. So we discovered that if one can combine two or more variation of sub-gradient and result into a more stable and effective method, then each individual method is still an open research area in optimization. And also, studying which area of knowledge can the combined sub-gradient method with built-in is also an open research area in optimization. So these are definition of some basic terms. This is our literature review. Some of the material we have. So this is our proposed algorithm. Recall, I say batch sub-gradient method. If you have 1 million records or 1 billion records, it consider all those records. It will load all those records at its memory before starting to initialize at which point does my fit line, if I'm dealing with just single parameter, intersect y-axis. If I'm dealing with multi-parameter, at which point will my plane intersect y-axis? So that is batch. It will load all the record, then continue initializing till it gets the best fit line. Or if you are dealing with multiple, till it gets the best plane. While we say stochastic is considering one data point at a time. So the proposed algorithm that we call Batch-stochastic Sub-gradient method, what it does, if we have 1 million records, then we are at the will to divide that record according to the capacity of what our computer, of our what data base warehouse. So we are good to divide it into 2, into 3, into 4, and whatsoever. We discover so far as we can divide it. So it will give, it will give us something meaningful or something that is better than batch and stochastic. So we design the algorithm. We say if we have 1,000 records, let's divide that 1,000 records into 10 batches. That is 100. We have 100 records, then load those 100 records, initialize the intersect of y and the angle. Then, after you have done so, try to find the line for those 100 records. Then free the memory from the first 100 loaded records. Then load the next record. Then link the results that you have obtained till you finish loading all 100 records. Then start over again till what? Convergence. So we say, let's test our algorithm using the same data that we have for the sake of explanation. So we have data like this. So we said using SQL, let's check the coefficient of determination of this data. Is there any noise in this data? If you don't have any noise, no need to optimize anything. If you can draw a line that will pass through each data point, so no need to optimize anything. But as we have seen under the figures that I have shown, let me take it back there. This figure, the downward figure. No matter we try to draw one line that will pass through all these data points, we'll discover that some data point will be out of that line. So we said we can optimize this one. So far, assuming that we can draw a line that will pass through without any data point being out of this line. So we say that data is in perfect shape or in perfect form. No need to optimize anything. So we say, let's analyze this data. After we analyze it, see our R square, which is 0.969, which is telling us that there is noise in this data because I did mean we have 1. That means our data, the coefficient is 100% accurate. So after we have this, we observe there is some little noise. So we say, let's take it into what? Let's set our learning environment. So we say batch subgradient method. We say batch, it considers the entire data set at once. So it considers the entire data set, load the data set, initialize, continue iteration till when B is 3,000, is that 7,500 and W1 is 157.5. It is at that point, then we take the capture of that. Then we will discover the next value, the next parameters of B and W1 that we will obtain, it will diverge. This one is the highest value, is the best intercept and the angle that it gets using batch method. So we say this is the iteration. If you observe here, this, I'm sorry. This is for batch, and table 3 for batch, and table 6 for stochastic subgradient. Sorry, here I make a mistake. It's for subgradient of stochastic subgradient capture. We say for stochastic, it is considering one data point at, so you have seen it. At each point, at each row, it is initializing the value of the angle of the intercept, the point at which our line intercept y-axis and the angle it makes. Then free the memory, then take the second record continuously like that. So this is stochastic. While the next one is batch, we have divided our data into 2. So you see, after it reaches the 4th row, then it will what? Reinitialize the parameters in convergence. So we make comparison for the 3 method. So you see, using SQL under R square, the first row, SQL analysis 0.969. And batch, when we carried the analysis using batch, so it gave us 1. That is, this is the highest convergence that it can go using batch, and stochastic also 1, and batch stochastic also that, and see the MAE, which is equivalent. So we say, let's move to the next data and see what will happen. So we inputted some testing data again. We say, let's call the first column age, and the second column weight, and the third column parent, while the last column be the intensity of systolic disease on infected person. For example, like this, the first row, with 54 age and 194 weight, and one of his parents has these said diseases. So this the last column shows the intensity of that disease on that individual. Likewise for the remaining record. So you say, let's analyze it using SQL. So you see it under R square, you have 0.70, telling us that there is about 30% inaccuracy in the observation or noise. So we said, using batch subgradient iteration, here we take the iteration I plus 6, see the B, the W1, W2, W3, and the MAE. So if you observe, you see under row I plus 10, we have the least loss value, MAE value, 9.4. So from there, you observe I plus 11, MAE started increasing. So telling us using batch method, this is the highest convergence that it goes. And at row I plus 10, you have your B, you have your W1, you have your W2 and W3, your coefficient. So also you say let carry our iteration using stochastic. So you see iteration J plus 5, J plus 7. If you observe, iteration J plus 7 has an MAE of 28.60. From there, the next iteration increased, it started diverging. So telling us using stochastic subgradient, this is the highest convergence it can go. So Batch-stochastic subgradient. So if you observe under row K plus 10, we have 9.44. So we say the model so far has learned and that it has predicted that the angle it makes is 34. Sorry, yes, the coefficient of the parameters 34.40 and this and that, where x0 is the age, x1 is the weight, x2, x2 is the parental history of the said disease. So as you inputted x0, x1, x2, x3, then it gives you the intensity of the disease on the infected person. So we say, let's make comparison of these three methods. So observe, as we have seen, we say batch method is the most stable method if you apply. While stochastic, because it's considering one data point per epoch or iteration, used to attract noises. So you have seen, we have under batch an MAE of 9.45, while for stochastic we have 28 due to what? The noise. And for batch stochastic, you see we have 9.44. So we say it, or we conclude that batch stochastic is the best. Why? Because we are able to divide our data into different warehouse. That is, we are out of memory issue and also have the stability of what close to batch. So we say batch stochastic is the best. Here again, like here in Nigeria, another example. We have Gombe State, Kano State, for example, and let's say Calabar. So these three states, maybe an individual have a house in each of the three states, and the consumption of the electricity on those three states, he based on the analysis he carried is the same. But unfortunately, he spent, let's say, 20 USD in the house A, 50 USD in house B, let's say 100 USD in house C. So if you plot those real space, those records, you observe that if you try to connect those three data points, you discover one will be out. So we said we want to, or the government, you said want, since those states are in close in the same region, we want if you are paying the same one in an individual, if he is paying certain amount for the consumption of electricity that he had in one place and also in his others, and so far the price shouldn't be difference. So that called for this optimization. So at the end of the day, you can try to sort all this. So in addition to that, the reason we make use of SQL in carrying this analysis, we observe SQL can store our record, and it can also work offline. It can take the record, save it till when we want to carry this analysis, maybe quarterly. It is during that quarter, then we will say the person that is living there, then connect your computer that is storing those records to the internet. Then behind the scene, we will be able to carry this. And then at the end of the day, those people that are consuming electricity, maybe you attach their email, then it will send them the expected price for the forthcoming month or year or so. So we said this method is the best, and there is no any other method that will give you these abilities. So, summary, we said MAE is the first discovered loss function, but doesn't have differentiable property. For that, scholars created another method, that is MSE. And after they created MSE, they discovered that MSE used to attract some noises. So they said, let's create root mean squared in order to penalize whatever we have at our MSE value. Then, during our research, we discovered that that first loss function, MAE, still has more computational efficiency than MSE or RMSE and RMC. So we adopted it, and with one go, we created Batch-stochastic Sub-gradient method. And we are able to test the stability and computational efficiency of our method using SQL. So we have conclusion. We have tested a lot of machine learning loss function. Then we discover that it's only MAE, MSE, and RMSE can fit well into training a continuous data. And no any other formal gimmick can one apply on continuous data that will give the most accurate prediction other than Batch-stochastic Sub-gradient method. We recommend development of high quality research level monograph on mean absolute error, mean square error, root mean square error, batch sub-gradient method, stochastic sub-gradient method. We also recommend having good graphs of why we make use of SQL or how SQL works. Lastly, we recommend choosing small learning rate, especially when we are near optimal point, because if we pick bigger learning rate, so we will likely be fluctuating around the feasible region. So future research. Say future research can consider implementation of batch-stochastic sub-gradient method software package and deployment of this package to neural networking, rainfall analysis, communication, and many other things. And also future research can consider creating stable and effective method for solving non-smooth, non-convex. We call under our scope, we said we are considering convex, non-smooth but convex. So future research can consider taking non-convex problem. So batch-stochastic sub-gradient, better computing time or better, yes, and less memory requirement than batch, because batch is considering the entire data set, and more stability than stochastic, because stochastic is unstable because it's considering one data point at a time. So we have developed a method that is less memory requirement than batch and more stable than stochastic, which is a plus to us. And the new method shows greater stability, accuracy, and convergence than any other existing method for minimizing continuous data with single or multiple parameter. Recall, I used to say single. If you have single parameter, that is, you are dealing with what? We are trying to find a best fit line. But when we are dealing with multiple parameter, we are trying to find out the best fit plane. So here are some of my references. So thank you for giving me this opportunity.